Hey everyone, it is me, Miss B, and in this video we are looking at the Unit 3, Lesson 12, Cumulative Practice Problems, and this is for Illustrative Math Geometry. So, to start out here, we are looking at some proportions, and we are given that quadrilateral ABCD is similar to quadrilateral A prime, B prime, C prime, and D prime, so we want to select all statements that must be true. So we're going to look at these one at a time. So I know I'm zooming in here pretty far, but it helps us focus on, what I'm actually pointing out here. So um, as long as we are being consistent, like comparing a prime version with its non-prime counterpart and doing the same on the opposite side of our equal signs, that is being consistent, and this would work for a proportion. So A is going to be one of our options. A would be correct. B follows this same pattern, except now our prime versions are on the denominator, and then the regular versions are in the numerator. But we're being consistent. We have non-prime over prime and non-prime over prime being consistent, using those same letters and organizing them in the same way. So A and B are both going to work. If we look at option C, so we have non-prime over prime, and it goes this direction. But for our other one, we have non-prime underneath, and we're going the opposite direction. So even though the letters are the same, we are not being consistent with how we form our equation here. So that is not actually going to give us anything correct. Option D, we actually do have consistency here, but our consistency is not necessarily up and down. It's going left to right. So I have my non-prime and then my prime version to the right. So AB in my numerator for both, and CD in my denominator, but I am using the original versions on the left, or the pre-image versions on the left, and then the image versions on the right. So this is consistent and this does work. For option E, though, we have this sort of like diagonal thing going on again, where I have two pieces diagonal from each other instead of left to right. Or they're actually just sort of in swapped places. So the left to right ones do work. This is A prime, D prime, and AD. But the problem is that for the numerators, we have the original versions and then the prime. Whereas down here in the denominator, we have the prime versions and then the originals. So this is not being consistent because if we go from original to prime, we're going in two different directions. So inconsistent and not going to be correct for that one. So A, B, and D show actual accurate proportions. Okay, that brings us to question 2. We have lines BC and DE, and they are both vertical. And then we want to know, what is the length of AD? So AD is our line here at the bottom. So AD, that's going to be this line right here, AD. So they want to know the entire distance. Now, they did tell us these are both vertical. Since they're both vertical, this means they're going to be parallel. And since we know that these line segments are going to be parallel, that means, or lines here actually, but that means that they're going to cut our triangle here into proportional sides. So I can use basically like this small blue triangle here for ABC, and then I'm going to use the large triangle, which would be outlined like here. I just can't really cut over top of things. So the one that's outlined in blue versus the one that's colored in blue, we have two similar triangles. So for the smallest one, we may compare 3 over 2. Actually going to get rid of these lines here. So I'm going to say 3 over 2. That's for the small triangle. That's the base over the height. And then for our large triangle, we want to be consistent and then do base over height. We don't know what the base is. We just know that that is AD. So that's our unknown. And then the height here on the right-hand side is going to be 5. And we just cross multiply to solve. So 2 times the length of AD is going to be 15, which means you divide by 2, and the length of AD is 7.5. And that is that question. So that brings us to number 3. Number 3 is a little tricky. We have a quilt made of squares with diagonals, and side length AB is 2. So they're telling us right now this side length is 2. Well, since these are squares with diagonals, I can also sort of label some other pieces here, like this length or these distances are going to be 1 each. And because it's square, we know that's also consistent for across the bottom here. This whole thing is 2, but each of these is now 1. So that's what we're told based off of what they gave us. They're squares with diagonals. So now let's actually look at what they want us to find. They want to know what is the length of BD. So BD is actually this diagonal right here across the middle. Now, in order to find this, we are going to use the Pythagorean theorem. Now, I'm not sure how much your classes may have practiced with this. Mine has not as much, but I actually went through this with them today in class. So we are going to use a squared plus b squared equals c squared. Or essentially, leg squared plus leg squared is equal to hypotenuse squared. And because this is a right triangle, since it is a square, we know that's a right angle in the corner. And I can say that each of the legs is 2, so 2 squared plus 2 squared should be equal to c squared. So that means c squared, well, 2 squared is 4, and 4 plus 4 is 8. So that means that c squared is 8. Now, that's lovely and all. The distance of that hypotenuse squared is 8. But I actually just want the hypotenuse itself, not the squared version. So that means we have to take the square root of both sides. That will leave us with just c. And then the square root of 8 is going to simplify because we can change it into square root of 4 times square root of 2. And this would be 2 square root 2. And so that is our distance for BD in terms of the length of our segment. It should be 2 square root 2. Now part B wants to know what is the area of triangle AEH. So AEH is this triangle down here at the bottom. They want to know what area does this take up. And so the dimensions here are 1 by 1. We're going to use our triangle area formula. So the area of a triangle is either 1/2 times the base times the height, or you may see it as area is base times the height divided by 2. Both of these are the same, but I like to use the equation on the left. So I'm going to use area equals 1/2. My base is 1, and my height is 1, so literally my area is just 1/2. and that's it. Um, but because this was my base here, or my base and height were these ones, that's how I know this is going to be half. And if you consider that this is just a square unit, yeah, it covers half of this square, right? Because if this is 1 by 1, this is 1 square unit. And so if this is 2 by 2, this would be 4 square units for the entire area. So yeah, visually, we can even just see that it is half of one of those squares. So it works out. That's going to bring us on to question 4 on the next page. We have this triangle, and we have segment A prime B prime is parallel to AB. So A prime B prime and AB, they have their parallel marks and everything. They want to know what is the length of segment B B prime. So B B prime, that is this one right here, just from one end of the segment to the other, not the entire length of a triangle here. So because, and I do like to like rotate my view a little bit, I like to think of the parallel lines as the bottom. So generally I would tilt my head a little bit to look at this one, because I like to think of the sides as actually being on the side, but those being the ones that we're splitting using a parallel line here. Either way, we're going to use the 7 and 6 here and make those proportional to our missing amount and our 3. So the work I would set up for this is that 6 over 3, or you could use 3 over 6. I have a tendency to use the triangle part and then the smaller chunk. So I am doing triangle over chunk. 6 over 3 is going to equal 7 over, and I'm just going to call this x, and we're going to cross multiply to find that amount. So 6x equals 21. We're going to divide both of these by 6. So that means that x is going to be 3.5. I believe this was a question on the homework from the other day as well, but that is 3.5, so actually your answer here is A. That brings us down to question 5. Elena thinks that BC, or the length of BC, is 16.5 units, and Lynn thinks it is 17.1. Do you agree with either of them? Explain or show your reasoning. Well, this is also a diagram from our previous homework. This is 4 and 2, which does not have the same proportion as 9 and 5. My guess is that either Elena or Lynn were using these sides as sort of proportions. So they were probably comparing 4 to 6, and then using that to compare 11 to this one. But because both proportions are not the same, we can't really even compare 11 to what the other side should be. Um, so I disagree with both. And I'm going to say the sides are not split proportionally. So we cannot use similarity to determine the missing side length. And that's it. We're just saying, hey, you know what? I don't think we can actually even find this at all because the sides are not split proportionally, so we can't really use any of these numbers here to find the missing piece. That then brings us to question 6. And Mai thinks she knows using the measures of two sides is enough to show triangle similarity. Do you agree? And explain or show your reasoning. Um, I'm gonna disagree. We know that two angles would show similarity. But let's actually draw a picture here. So I'm gonna say disagree. And it's almost the same way that two side lengths wouldn't necessarily even give you enough to be congruent. The explanation I like to use for this is an isosceles triangle that'll have vastly different angles. So maybe one isosceles triangle that's like really wide, like this, and has really narrow base angles versus like a really tall triangle that's still isosceles. Because this is like saying, this is like the proof that says that like all isosceles triangles are similar because they have two sides proportional. Even if we said that this was like 3 to 1, the angles make a big difference. And so we can say, well, oh, didn't mean the eraser. I'm going to show here and here as being congruent, and then like here and here as being congruent. So I am establishing I'm using isosceles. I'm going to say disagree. And what else can I show on my diagram here? I don't know if I need to show anything. Yeah, I'm going to say disagree. For good measure, though, I will say angles are important in triangle shape if not all three sides are known to be proportional. So if we only know two sides, we're going to need to know some angle measures because if we knew all three sides, that would prevent this situation from happening where the base of the isosceles triangle is either very, very big or very, very small with the then isosceles parts being either congruent or similar. So yeah, angles are important if we don't know all three sides. If we knew all three sides, that would prevent this um, version of what I drew from happening. Okay. Then question 7, we have line G is dilated with a center of dilation at A. Okay, center of dilation at A. A is here. And then we are talking about line G. That is this line here. And they said the image is F. Approximate the scale factor. Well, if we are dilating, we're going to be moving this line. Basically, we're comparing the distance between A and then the 2 points I just drew. So this blue line is about halfway between A and the green line. And since we are going from A, and the image is this green one. We're actually going from the blue line to the green line, which means our scale factor is going to be 2. Now, if we were going from the green line to the blue one, we would use 1/2 or just the reciprocal of that. So I would say um, approximately 2, because it did say approximate the scale factor. So approximate is appropriate. And yeah, this is the end of this assignment, 7 questions. So this has been Unit 3, Lesson 12, Cumulative Practice Problems for Illustrative Math Geometry.